So the first page, worth 1 point apiece, like I'm on a game show. And I kind of told you that some of these were going to be on there. So I'm, like most teachers, kind of reflective, self-reflective about kind of when I test you, how you do. And I told you this was going to be on there, you know. Conditions, standard conditions for gases are different than for thermodynamic problems. So there's a temperature and a pressure component to both. For thermodynamic problems, it's 25 degrees Celsius and 1 bar of pressure. That's the little knot, the standard state. When we say something's a state function, that means it's independent of path. It depends only on the final and the initial value. Question C, and I kind of gave some latitude here, but what I was really after is kind of the going all the way when we talk about a system being isolated or closed. Within that, what's in that system stays within that system, whether that's energy or matter or momentum. So that's C. Questions D and E. Question D said, if you have a heat of reaction that's negative, basically, is that endothermic or exothermic? And it's exothermic. The next question kind of related to that, if you have a positive heat of reaction, that means that your heat of reaction is endothermic, so actually that must require energy. F, I gave you the specific heat of two metals, copper and aluminum, and I asked you if you apply the same amount of heat or energy to both, which one is going to reach the higher temperature? And it's the one that is least stubborn. It's the one that has the lower specific heat. So this is to say that you only have to pump copper with 0.385 joules of energy in order to get it to budge 1 degree Celsius. Aluminum is more stubborn, so copper actually will end up with the final higher temperature. Yeah, higher final temperature. G, give an example of a physical phase change that's exothermic. So that's one where energy is released, so bonds are being formed. So you have some options there, gas to a liquid or liquid to a solid, or you could do sublimation, a gas to a solid. Bonds are being formed. Kind of opposite of that is H, an example of a physical phase change that you need to break intermolecular bonds. So that would be melting, where something goes from a solid to a liquid, evaporation, something going from a liquid to a gas, or else something subliming again, going from a solid straight to a gas. Question I and J were kind of related. I wanted to know which physical phase has the least amount of kinetic energy, and that was kind of that table that we brought back in from clear Unit 1. In Unit 3, we're looking again at the states of matter. And something in its solid state has the least amount of kinetic energy. Kind of related to that also, which one has the most amount of motion? That would be gases. I always think of that little girl running around the room. These were each worth 4 points apiece, and you did have to show your work for these. You didn't have to show your work for the previous one. So I kind of drew a picture of a system, and we were given an energy term and a work term. And it says that the system gains 133 joules of energy. Then it says that the system does 240 joules of work on the surroundings. So actually the work term is negative. So you add those together and you come up with negative 115 joules. The next one, again, you need to show your work. Given this information, we should be able to find the specific heat of a substance. So we're given mass, Q, energy, and the delta T. So rearranging for Q is equal to M C sub P delta T. Of course, C sub P is the Q term divided by the product of the mass times the delta T. So rounded to 3 sig figs, 0.190 joules per gram degree Celsius. C, that was where you were given the heat of vaporization for cyclohexane. It requires 30.0 kilojoules of energy per mole to go ahead and get that to go from its liquid to its gaseous state. And how much energy do you need to go ahead and vaporize 25.0 grams of cyclohexane? So of course you're going to need to convert that mass to moles ultimately. So that's what I did down here, convert mass to moles using the molar mass of cyclohexane, and then went ahead and plunked in the heat of vaporization. Rounded to 3 sig figs. You need to pump it with 8.91 kilojoules of energy. D of this exam, D and question number 7 are the only two that I'm like, oh, wow, that's pretty cool. They'd have to kind of do some thinking for that one. So there were a few of you out there that actually got 2 out of 4, but nobody got 4 out of 4 for this particular question. We talked about the standard molar enthalpy of formation. In fact, we just went ahead and in lecture, we came up with writing the equation for the standard molar enthalpy of, I can't remember what it was benzene or something. So here they're wanting the standard molar enthalpy of formation of ozone. And up there, we're told that ozone is O3. So basically, one of the first things you need to do is come up with the standard molar enthalpy of formation of ozone. And we said that's the formation of 1 mole of whatever is of interest, in this case, ozone, from the, from the elements in their standard state and standard conditions. And for oxygen, that's O2. So we've kind of talked about this. How would you get 1 mole of O3 from kind of paired up O2 molecules? And if you take 3/2 moles of O2, you will get 1 mole of O3. So you had to come up with this as the equation and then link actually this to what you were given the heat of formation of. So instead of given the heat of formation of 3/2 O2 to go form 1 mole of O3, you are given kind of the reverse of that, okay? 3 moles of O2 instead of 3/2 moles, and it's reversed. So basically we have to take this times -1/2, and there you go. So yeah, that was probably interesting. Then we had a series of questions, each worth 6 points. And some of these, you know, I really think that if it weren't a test, and I don't know how to take the test out of tests, I honestly think if it weren't a test, you guys would have gotten it like that. Okay, so this one worth 6 points, and number 7 was worth 6 points, right? Okay. So here it says calculate the energy if you are going to go ahead and react 45 grams of NH3, knowing that for every 4 moles of NH3 you react, you release 906.2 kilojoules of energy. So one of the things we need to do is convert that mass to moles. So we need to knock out the molar mass of NH3. And I went ahead and used that then. I actually, my first term and my third, I probably would take my third term and move it to my second term, but it all works out okay. So you take the mass of NH3, okay, and I probably would put the molar mass there. That would get me to moles. And then recognize from that particular equation, like I said, 906.2 kilojoules of energy are released per 4 moles of NH3. So that's a negative 599 kilojoules of energy are released with that mass. The next one was Hess's Law. Everyone loves Hess's Law. Yep, and I really like the drawing the line and everybody draw right behind this, okay? It helps you, and actually it helps me a lot, because in the past I've had like scribbles up there. I'm like, what? So clearly kind of what I usually do on my answer keys and actually in lecture is I make for each puzzle piece, the 1, 2, and 3 up above, I make a 1', 2', and 3'. And I manipulate 1, 2, and 3 to, in my best interest, to get the equation of interest, which the equation of interest is that NO plus O goes to form NO2. And however I manipulate those equations, I also have to manipulate the heat of a reaction. So for the first one, 1' is 1, okay? If you focus on the NO, okay, in the equation of interest, we have 1 mole of NO on the reactant side. So I'm just going to leave it alone. Okay, so I bring down the heat of formation of 1' is the negative 198.9 kilojoules of energy. Looking at the puzzle piece 2, notice that if you focus on the yeah, we need to get rid of something, don't we? If you focus on the O3 that's introduced in 1, you need to get rid of that 1 mole of O3. So however you want to, that's how I looked at it. To get rid of my 1 mole of O3 that I introduced here, okay, I'm going to have to reverse this thing, and actually instead of 2 moles, I only want 1 mole, so I'm going to reverse it and take it times 1/2. Doing that, I also then need to take the heat of the reaction and multiply it by a negative 1/2. For the last one, we're back to just going ahead and looking at on the reactant side of the reaction of interest, I have 1 mole of oxygen And puzzle piece number 3, I have 2 moles of oxygen on the product side. So I'm going to go ahead and reverse it and take it times 1/2. So I have to manipulate the heat of reaction similarly. So then once I have these heats of reaction, as long as, and it does, if you add up 1 prime, 2 prime, 3 prime, you do get the reaction of interest, then I can go ahead and sum the heats of those reaction. And rounding it to 1 decimal, it's negative 304.1 kilojoules of energy. This one, I told you there'd be one of these too, okay? Had to read it a few times because kind of in paragraph form, it kind of confuses me a little bit. But this was actually just using the standard molar enthalpies of formations of the reactants and the products and using that little equation that we have up here, this one right here, okay, to come up with the heat of that reaction. So if you read it a few times, for instance, you will see that, let's see how do I do this. You will see that with regard to the HCl, that isn't what I want. Let's see this one. With regard to the HCl, the standard molar enthalpy of formation is negative 92.3 kilojoules of energy per mole. So remember, then we take this stoichiometric coefficient of 3. Okay, I'm going to focus on the products first because that goes, it's always final minus initial, products minus reactants. So I kind of pulled out standard molar enthalpies of formations of both the products, of both the reactants. Of course, as it says up there, the standard molar enthalpy, or it doesn't say what the standard molar enthalpy of formation of Cl2 is. It simply says that Cl2 gas is in its standard state. So the standard molar enthalpy of formation is 0. So once you have the summation of the products, from that you subtract the summation of the reactants, and this is where it's really easy to drop a negative sign. Okay, so bottom line, this approach, we get the standard molar enthalpy of formation. Using this approach, we get the heat of the reaction is negative 305.2 kilojoules. Right. This one should have been kind of similar to what y'all did for your lab. Basically, you're dissolving, instead of ammonium chloride, you're dissolving ammonium nitrate. Okay, so, and the water is getting cooler, just like your ammonium chloride you did in your lab. So like I said, it's very similar. You're given enough information to come up with the Q of your solution, okay? And it's an isolated system, so the Q of your reaction is equal to negative Q of your solution. Q of the solution, using the mass of the solution, the specific heat of the solution, the delta T of the solution. The Q is negative 400 joules. But I wanted to show 2 significant figures, so I wrapped it up into scientific notation. Then the Q of the reaction is that number times negative 1. So I went ahead and at this line converted it to kilojoules. So it's 0.40 kilojoules. And then we need to get it per mole of ammonium nitrate. And so we need to go ahead and knock out the molar mass of ammonium nitrate up there at the top there, 80.05 grams per mole. Divide the energy per the mass, and then go ahead and insert the molar mass of ammonium nitrate, and that gets us in energy per mole. So 27 is the answer there. Like I said, worth only 6 points. Okay, I think this one was a lot harder than the few problems ago. This one actually, if you read it a few times, and it was similar to one of the ones that was end of Unit 3, it actually has four Q terms. You're like, really? Basically, we have a small amount of ice, 9 grams of ice, that is going to go ahead and melt. It's at an initial temperature that's colder than the freezing melting point temperature. So we basically have to go ahead and warm it from negative 10 to 0, and then we have to go ahead and melt it. And then we're going to go ahead and take that now water, and we're going to cool that water down. No, sorry, we're going to warm that water up to some final temperature. And the final temperature was given as 78.2. So these 3 terms right here all deal with 9 grams, okay? This other term right here is the coffee that is cooling down, okay? So you kind of see down here chipping away at each one of those terms. This first term again is your ice warming to the freezing point temperature. This one right here is your, oh, sorry, this one right here, kind of in the middle of the page, is applying the enthalpy of fusion. And actually, you kind of see some marks here. I grabbed the wrong delta H. So when I first did it, I grabbed the 2.26 times 10 to the third instead of the 33. So I had to go back and correct everything. So that's the amount of energy that's required to go ahead and melt your 9 grams of ice. This then is your 9 grams of ice that is cooling down to your final temperature of 78.2. Okay, and then this last one is actually your, the mass is what you're solving for. And it said use the specific heat for water as your coffee is 4.184 joules per gram degree Celsius. So the change in temperature is this initial temperature, change is always final minus initial. So this actually is the 78.2. From that you subtract the 90. That's what the negative 11.8 is. So we're solving for the mass here. And I went ahead and I don't like algebra any more than anybody else likes algebra, but I can rough my way through it. So I went ahead and kind of cleaned this up by multiplying these terms together, making sure that I keep my units, and keeping my units degrees Celsius cancel here, and I'm left with joules per gram, okay? And it actually negative value here times the mass of the coffee, which we're solving for. Whew. So I should have 4 energy terms here. Okay, this was the energy of the solid cooling down. This is the energy of melting the solid. This is the energy of that liquid ice then coming to the same common temperature. And this is the energy associated with the hot coffee cooling down. Okay, and mass is what we're solving for. That's all set equal to 0. Rearranging, just trying to isolate the mass all by itself. We collect the terms that don't have a variable in front of them. So that would be these 3 terms. This is the way I do it anyway. These 3 terms, and move them over to the other side by themselves, give you 6,100 joules is equal to that 49, and I got rid of my negative sign too. That would have been negative, the negatives cancel. 49.4 times the variable we're after units, we still have our joules per gram. So, ready to go ahead and isolate the mass by itself. We can divide both sides by 49.4 joules per gram, of course. That's a wonderful thing because we have joules up here and joules per gram here. The joules will cancel, and of course we have units of grams in the inverse of the in the denominator of the denominator. That actually means that they're units of grams in the numerator. Rounding to 2 significant figures because I've carried 2 significant figures in this energy of 6,100 joules. So 120 grams is the amount of, is the mass of your coffee that you must have had at that initial temperature to cool down to that temperature, being as you melted 9 grams of ice. So, yeah, that one was